So hello and welcome student to the today's lecture of the course MA412 Linear Algebra, and today we have this is lecture number 9. It's number 9. Okay. Now I recall in our last lecture, what we learned about this space of linear maps and linear operators, algebra linear operators. So for the space of linear maps is what? So this is the symbol LVW, which is space of linear maps. So what is that? So this is collection of all linear maps from V to W. The T is linear. Okay, and then we showed that this forms a vector space with respect to addition of two linear maps and scalar multiplication, right? So that we know, but the natural question is that you can ask natural question that if we know that if it is known that dimension of V is finite and dimension of W is also finite, suppose this is known, then what is dimension of this LVW? This is a natural question one can ask. Okay, and to answer to this question, we have the following theorem. So what does the theorem tells you? So let us assume that it's at this dimension of V something say n, and dimension of W say m. Okay. So this is, if we assume this thing, then this special linear operator maps from V to W is actually isomorphic to this space of matrices of size m cross n over the same field F. Okay, so F is the underlying field where V and W is over F. Okay, so this is so this is the theorem, and that theorem has also consequences which tells you that dimension of this space of linear maps from V to W is exact formula. Okay, so now let me start with that proof. So how do you prove this kind of theorem? So obviously, if you prove something is two spaces are isomorphic, so you need to find out linear maps which is invertible, right, among them. So how to define it? So let me first define two matrices to basis. Maybe that will be helpful. So let V1 say is V1, V2 dot Vn be a basis of V, and let me write down V2, which is U1, U2 and UM. Okay, be a basis of W, because W is dimension M, so I wrote M vectors right inside V2, and similarly for V1. Okay, so if this is the matrix of these things, then we know how to write down that matrix representation for a linear map from V to W, right? So I am going to take help from that representation only. So then what we'll do? So we'll define a map, say psi from this space of linear maps from V to W to these matrices, special matrices, M cross N matrices over F. By what? So you take a linear map, and then what will the image? The image will be the matrix, and the natural matrix here is what? It is the matrix representation of the linear map with respect to the basis B1 to B2. Okay, and you check that this is actually M cross N matrix, so this is the element of M cross N over F, right? Because this is a matrix whose order is M cross N. Okay, and this map is obviously a linear map. You can check that. So this number one, this I is linear as I is to psi of T1 plus T2, that has to be equal to T1 plus T2 with respect to the matrix basis B1 B2, and that you proved last day that this is nothing but B1 B2 plus T2 of B1 B2, right? And this is obviously psi T1 plus psi T2, right? Similarly, for scalar multiplication, for any t, A is nothing but c times t with respect to this basis, and this is nothing but c times t, which is nothing but c of psi of t. So psi is linear, there is no problem with that. Now, so we need to prove psi is also bijective map, right? Injective 1 on 1 2. So injective also is easy because okay, so yeah, so if psi of say T1 equal to psi of T2, suppose, so that means what? That means the matrix representation is same, right? So the matrix representation of T1 will be something B1 B2, which is same as for T2 B and B2. Let me write down this is matrix Aij, and this is matrix Bij. Okay, they are same entry wise. Okay, but what does that mean? That means that means that is T1 of Vj. So what are the bases? So let me check it again. V1 Vn and yeah. So T1 of Vj is nothing but summation Aij Ui I equal to 1 to m, right? But Aij equal to Bij for into wise they are same. So what does that mean? That means you write down Aij by Bij, and then Ui I equal to 1 to m, and that tells you this is nothing but T2 of Vj. So this map with T1 T2 are agree with these two for all j, as obviously for all j equal to 1 2 up to m, and hence they are equal because they are same on the basis vector, they are equal, right? So this is, so what does that mean? That means size 1 1. Okay, and for onto what you need, so for onto property what you need, so you start with the element. So let's say matrix A, maybe say Aij, element of m cross n over f. You need to find out a pre-image of that under psi, right? So then how to define? So you define the map T of Vj by this summation Aij ui I equal to 1 to m, right? Now if we write down that, we remember from last class, so this will be a linear map, so it sends Vij to Wij, and there will be only, sorry, Uij, and there will be only one such linear map, unique, right? And then if you want to find out what is the matrix with respect to b1 b2, and you see that is exactly Aij, which is exactly equal to A, and hence that pre-image of A is nothing but this T, right? So what does that mean? That means size onto, and size 1 and onto, so that tells you that size is a size and isomorphism between those two spaces, and hence they are isomorphic. LVW is isomorphic to M cross N if they are isomorphic. Okay. Now, what are the consequences? So, if they are isomorphic means what? That means they have everything same, right? The dimension is same, everything is same, and then what was our original question? You can get the answer, right? So, what was the original question? Then what was the dimension, right? So thus you can say that dimension of LVW is nothing but dimension of this matrix space. Now recall, for matrix we discussed that the elementary matrices forms a basis, and there are exactly m cross n elementary matrices, so this will be actually m into n, right? And hence this is what is m? M is nothing but the dimension of V, and n is nothing but the dimension of W. Okay, so the dimension of LVW is nothing but the product of the individual dimension when V and W are finite dimensional. Okay, so you can easily find out these results. Okay. Okay, so now also you recall we also discussed about something called standard representation, and that actually gives, say that the standard representation vector space, representation of a linear space V that gives an isomorphism, right? Isomorphism so I'm assuming that V is finite dimensional, right? So yeah, so maybe dimension of V equal to say n, isolation from V to Fn, right? What was the map? So you define phi with respect to some basis, say B, and you send the phase vector V to the coordinate vectors. So the coordinate vectors of V, and this will be kind of a column matrix. Okay, so this is the element of Fn. So this will also tells you that any two vector space of dimension. So you can say that thus any two vector spaces of same dimension are isomorphic. So what does that mean? That means you have V, you have W, and you have this is Fn, both of dimension same. Then you have here with respect to some basis you have this something, say phi or psi, whatever, some b dash here. Okay, the isomorphism. Then these two are actually isomorphic. So how to go? So if coming from here to here and then take the inverse, this isomorphism inverse exists, take the inverse here. So this will be phi b composed psi b dash inverse. That will be mapped from with the which is then isomorphism, right? This is one such maps you can find out. Okay. So what happens if you don't have dimension same, then what happens? So in that case, suppose you have V and W, and you have a linear map T. Is an element of LVW. Okay, and we know the dimension of this say n. So we have a natural map which is called standard representation from V to Fn, and natural map here also V to Fm. The dimension is n and m. So this is phi b. This is maybe write down phi b dash, whatever. Okay. Then the question is that do you have a natural map from here to here, Fn to Fm, such that similarly the last result, the diagram also commits here. So these are called commutative diagram, means you can from here to here you can compose a map and come Fn. Similarly, from composing a map with T come to Fn. The answer is yes. So what is the map? This map is called LA. You define it. I already defined it last time. So LA is what? So it's sending a vector S V column vector n and sending it to a column vectors in Fm, right? So this is a map. This is called left multiplication, left regular multiplication, something like that. Left regular representation, and you can easily check that. If you go with T and then go with phi b dash, that's nothing but going with LA and then phi b. Okay, and these are called commutative diagrams. Commutative diagram. So what does that mean? That means no matter from which road you choose, you start from B and coming to Fm, you will reach if you choose this path or this path. Okay. So so this composition of these two are same actually. You can find out. So with some example you can find out. Okay, so maybe so this was that remaining thing which I was planning to do. Now question is that so now we learn a new idea, and this is called change of as a coordinate ordinate matrix or change of basis matrix, whatever you can say. So some people call it change of basis matrix, some people call it change of coordinate matrix. Okay, doesn't matter. Okay. So what is that? So now recall that when we define these maps, we said that this matrix representation always depend on a basis, right? So if you change the basis, then obviously you will have a new matrix for that, right? And how to find out what are the matrices and how they are related with that? That is the topic of this part, change of basis matrix. So let me start with say so let I from V to V. V is a finite vector space over some field F, and you have a identity B, the identity map. Suppose it be identity map, right? So what does that mean? That means I of V equal to V for all V belongs to capital V, right? Identity map. and this is of the linear map, and it's also invertible. So this is isomorphism. You know that, right? It's simple. Now, if you choose two bases, for example, so let you have two bases. So let say B and B dash B, two bases of V. Then question is that if you want to change from the basis from B dash to B, so what does that mean? That means you want to write down that basis vector of element of B dash in terms of element of B. So you're changing from B dash to B, and then what will be happening? So obviously, if you write down two bases, then there will be a matrix, and let me write down this matrix Q as I, changing from say B dash to B. So this is I'm giving the symbol. You can choose other one also, B to B dash has no problem. But let me write down this is Q. So then what does that Q do? So Q actually so what does that mean? That means you write down every basis. Okay, let me write down basis element also. Maybe so B is maybe V1, V2, and Vn, and B dash maybe U1, U2, and Un. Okay. So what does Q do? Q change from B1 to B. So what does that mean? Then Q actually sends so that if the I of U1, right? So U1 means U1 itself because I identity that you are writing in terms of these elements. So let me write down Q is probably Qij. Okay, and then this is nothing but Qij into Vi, and this is I of Uj, I equal to 1 to n. Okay, so this is clear. So it's changing from B dash to B, right? Change the basis matrix. Okay, so now the property, what's the property of Q? So the first property Q is actually invertible, and why such? Because Q inverse is nothing but if it exists, then it has to be I this, right? So beta has to beta whole inverse, and this is nothing but we already showed in last lecture. This is nothing but beta to beta dash. Okay, but I inverse exists because I is an invertible linear operator, the identity map. So Q inverse exists. So Q is invertible. That is obvious, right? Okay. Yeah. So far good. And the other property what says that why this is called Schindler basis matrix, that we will see that property 2. So for any if you choose any vector V in V, and so you have two coordinates with respect to two different bases, right? So if you have two coordinates with two different bases, then you can write down this V with respect to the basis B is nothing but just V with respect to basis B dash, and then the X amount Q on that, so Q times that. Okay. And the proof is also not difficult. So you have V in this left hand side, but this is also the image under the identity map, right? But we know that if you have if you want to know the image of linear maps with respect to basis, that is enough with respect to this, right? So V with respect to b dash and then b dash to b of I. Okay. So you have the coordinate vectors and then you change it from b dash to b, so you will have new coordinate vectors. And this is nothing but q. This is q times v of b dash. Okay. So that so this is very important thing, and so let me define properly. So definition. So definition. So this the matrix is Q, which is of this form I b dash to b. This is called the change of coordinate matrix. From b dash coordinates to b coordinates. Okay, and thus the q bar actually q inverse actually change the basis from b coordinates to b dash coordinates, the opposite one. Okay, b needs to b dash coordinates. So now we will give some example, and let's see what is happening actually here. So example. So you have, let me choose these R2 over R. Okay, and let me choose two bases. One basis is this b is say 1 1 and 1 minus 1, and b dash is 2 4 and so 3 1. Okay, so let me find first q which changes b dash to b. So what does that mean? That you write down the basis vectors of b dash in terms of basis vector of b, and this is nothing but write down 2 4 in terms of these. So how do I write down 2 4 in terms of 1 1 1 3? So this is minus 1 you can put here, so 3. Okay, so 3 into 1 1 plus minus 1 into 1 minus 1, right? So that tells you that 3 minus 1 equal to 2 and 3 plus 1 equal to 4. Similarly, for 3 1, what we will do? 3 1 3 plus 1 2, yes, so 2 into 1 1 plus 1 into 1 minus 1, right? 2 plus 1 3, 2 minus 1 1, and hence your q is nothing but matrix 3 minus 1 2 1. So this is your q, right? And this change the coordinates of with respect to 2 4 into coordinate to this, right? So whatever the coordinates beta dash coordinates, you can change it to with respect to q. If you multiply by q, it will change it to b coordinates. Okay, so what does that mean? That means for example you write down this 2 4 in terms of this beta dash coordinates and multiply by q. Let me write down b coordinates. What is the 2 4 of b coordinates? So 2 4 of b coordinates will be q times 2 4 of this beta dash coordinate. So q is what? Q is nothing but 3 minus 1 2 1, and the beta dash coordinates of 2 is what? So I mean beta dash coordinate 2 is means it's 1 0, right? Always, because when you write down 2 4 in terms of beta dash, so it will be 1 and 0 obviously, right? It's 1 0. Okay, so you better to write down actually all in column vector. That is better actually. This is also column vector. But then what is this? So this is 3 into 1, and this is 3, and then minus 1 into 1, so minus 1. So this becomes this in terms of so this becomes this in terms of so in 2 4 with respect to beta coordinates was 1 0, but with respect to beta coordinates become 3 minus 1. Okay, and then obviously you can talk about the converse, how we can go to d beta, that is we need to multiply by q inverse. Okay, now the natural question one can ask that what happens if you just take any linear operator on V, then what happens? Then for linear operator, are there any relation among those t and t with respect to a basis and other basis? The answer lies in the following theorem. What is the theorem? So that you have linear operator on V. Okay, and so you have say 2 bases, so B and B dash 2 bases of say some finite dimensional vector space V. Okay, then you have 2 matrices, one with respect to B, another with respect, this is with respect to B dash, and another with respect to B, and the relation is that they are linked with this change of coordinate matrix. Okay, and obviously if you know this, then you can say that this same as T B will be just multiplied from left side by Q, so Q times T B dash multiply Q inverse from right side, so Q inverse. They're same. Okay, so now obviously this requires a proof, and proof is also not so difficult. So how do you prove this kind of statement? So what I need to prove? I need to prove that, okay, so I will prove that T B dash in terms of this. So sorry, Q B dash. So you start with Q T B dash. Okay, and we know that Q is nothing but I, right, from B dash to B. Now from B dash to B, and T B dash means T, actually that means that T B dash B dash. When I am saying T B dash, I mean with respect to the same basis both sides, and hence this will be nothing but I times T B B dash B, right? Now note that the I is the identity operator, and it has the property for any operator T I T equal to T equal to Ti. So IT and Ti is same, kind of commutes. So identity commutes to the every operator, right? And then you can write down this is as Ti of B dash of B, right? And T of B dash of B means what? So is I is from B dash B and T to B with respect to B, BB. So BB means what? BB means is B with the same matrix, same basis, but this one is nothing but Q itself, right? And hence what I was trying to prove, that T B dash not B inverse, TB dash. So will be nothing but Q inverse TB into Q. Okay. So this completes the proof that the relation between the matrix representation of the linear map with respect to two bases, and they link with the change of basis matrix, a change of coordinate matrix. Okay. Now let us see this with an example, proper example. Then we'll have more understanding on this. So let me again example. You can start with that same vector space R2 over R, and we have the same basis we already discussed. Let me write down 1. So 1 Q, 1 1, and 1 minus 1, and B dash is what? 2 4 3 1. Okay. And Q, the change of basis matrix from B dash to B, that we already find out what was the matrix. 3 minus 1 2 1, right? And hence Q inverse will be what? So 3 plus 2 5, so 1 by 5 is that determinant here. Okay. And then how to find out? So this change 1 to 3, and this minus plus, and this minus, right? For two cosine matrices, this is the way to find out the inverses. Okay, so this is done. Now we want to verify this statement what we proved. So let us find out that what is TB. Okay, so what is TB? That we need to find out. So to find out TB means what? So that means we need to write down that. So TB means B to B. So write down that basis with respect to basis vector B. What are the images? So this vector is 1 1, right? So T1 1 is what? Okay. Okay, I did not define here T. So for let me define a T here. Okay, then you will have. Let me define an operator T. Okay. So maybe you define T from R2 to R2 by you choose something, say V1, V2, and send it to 3V1 minus V2, V1 plus 3V2. Okay. Now you can ask what is this basis with respect to B. So B is 1 1. Then if you follow this, then 3 minus 1 2, and 1 plus 3 4. So 2 4. 2 4. 2 4. Okay. Now how to write down 2 4 in terms of matrix? So in terms of this basis vector. So this is 3 times 1 1, and then minus 1 times 1 minus 1, right? Then 2, yeah. So similarly, if you go with T minus 1 and this, and with this, so 3 minus 1 is 2, and this is 1 minus 3, it's minus 2. So that's maybe 3, 3 into 3, and then minus 1. Minus 1 is plus, and minus 1 is plus 1, yeah. So that will gives you 4, and here minus 2. So 4 and minus 2. And it will be, this will be 1 and 3, yeah. So 1 times 1 1, and then you have 3 times 1 minus 1. So you see that 3 plus 1 4, and 1 minus 3 minus 2, right? And hence the basis of T with respect to this basis, matrix of T with respect to this basis will be what? Nothing but 3 minus 1 and 1 3, right? Now, if you know these things, then you can obviously talk about what is t respect to b dash. I know that t respect to b dash is nothing but q inverse this t with respect to b and then q. Okay. Now you just do it. So what will be that then? T with respect to b dash is nothing but minus 1 by 5. Sorry, 1 by 5 into 1 1 minus 2 3, and then b dash what we got 3 minus 1 1 3, and q was what 3 minus 1 2 1, yeah 3 1, yeah. Now you just multiply all those things, and then your final answer will be 4 minus 2 1 2. This is how one can multiply. Okay, that is multiplication. And this is also, you can easily check it from the definition. So how to check from definition? So to check with respect to basis b dash, what you need to do, you need to find out what is the value of t in the basis vector, which is 2 4. So 2 4 was what? So 2 4 was 2 times 3 times 2 means 6 minus 4 equal to 6 minus, yeah, 3 into what was the map? Let me see. 3, yeah. So 2, if you put 2 into 6 minus minus 4 is 2. So this is 2. And then 3 into 4, 12 plus 2, 14, right? Now how to write down these in terms of the same basis? So we write down 4 into 2 4 plus or rather minus plus minus 2 into 3 1, right? Then you'll have what? Then 8 minus 6 equal to 2, and 16 minus 2 equal to 14. This is the answer. Similarly, for other one, 3 1, what is the answer? What is the image? Image will be 3 into 3, so 9 minus 1, which is 8, and 3 plus 3 into 1, 3, so 6. And this will be what? This will be again nothing but 1 times 2 4 plus 2 times 3 1. And you see that 3 into 2 6 plus 2 equal to 8. 4 into 2 4 plus 2 into 1 is 2, so 6. This is actually matching. So the matrix representation is actually the same, this one. Okay, so they are matching each other. Okay, so now with the help of this, so now we will define one final things for today's lecture. So let you have two matrices A, B belongs to same order, so n cross n matrices. Otherwise we can't talk about the inverse, right? Over the some field here. Then so A and B are said to be similar over if we generally say the same field. Okay, if there exists a matrix say Q, I should say also invertible belongs to that the same order space, such that what happened, the equivalent B equal to Q inverse A Q. In this case, we will say that A and D are similar matrices, similar. Okay, and note that that matrix we got for with respect to bases, they are similar. So these and these are similar matrices. Now again, you also can see that similar matrices actually define the equivalent relation on M of n that n cross matrices. Okay, specified n cross matrices. It's obvious because any matrix is similar to himself. You choose Q equal to I identity, that will enough, right? So that means that this relation is equal, it's reflexive, right? So that similarity, not that the similarity is an equivalence relation on that special matrices. This is simply reflexive symmetry and transitive are simple, right? Okay, so maybe we will stop here for our discussion. Next we also will learn a very new idea. Okay.